Good afternoon, everyone. I'm Professor Tanya Schmutzer. I'm Director of the Institute of Advanced Studies. Welcome to the International Hub. It's wonderful to see so many of you today here. This is great, almost full house, given how empty the campus is. We're probably the busiest space on campus today. It's great to see those of you joining us online. Welcome. So here at the IAS, as many of you know, many familiar faces, we host the conversations about the most exciting things, about the most amazing things. These are the conversations about research that get us all thinking and kind of debating and discussing. And so it's wonderful that today we are able to host and to welcome officially Lucy, who is our Fulbright Fellow. So as Institute of Advanced Studies, we don't just host IAS fellows who are coming through open program and residential fellowships, but we're also home to our international fellows who come funded by different external programs. And so whether they want it or not, they become IAS fellows. There's no opt-out option, I don't think. No one has complained yet. So welcome, Lucy. It's really, really nice. It's almost 2 months, 3 months?
More than 2 months.
More than 2 months. Yeah, like I feel like we've kind of spoken when you just came, and it's just wonderful that you've been here all this time. So a couple of housekeeping rules before I pass to Lucy to present. We are recording the presentation, but not the Q&A. So when after the presentation, we will be taking comments, questions, just feel free to ask whatever you want within the limit of the presentation. We will not be recording that. The presentation will be released on our YouTube channel and also as a podcast. For those of you online, please post the questions or comments in the Q&A section of Teams. We are monitoring that, so we'll pop it on the screen when time comes. Lucy, over to you. Thanks so much for coming.
Standing in the right spot. Okay. All right. Well, thank you all for coming in the middle of the summer, and I'm sure you have more fun things to do, but I'll try to entertain you. I'm very happy to be here. I've been here for about 2.5 months, and I have a few weeks left. It's down to the dregs of my experience here. And it's been absolutely amazing. I've learned so much about this university and about my topic area and about some of the things that a few of you do. So I'm really grateful to have had the time here, and I'm going to share a bit of that with you today. I'm here through the US-UK Fulbright Commission, so I'm also very grateful for that funding that made it possible to be here. So today I'm going to talk sort of more generally about what I do, and a few of you are specialists. So if there's topics that we want to dig into in more technical depth, we can do that with questions. But I wanted to kind of give an overview of some of the work that my lab and I do in smart clothing, and kind of along the way give you a sense of some of the reasons that this domain is challenging. So some of the big problems, big questions that contribute to the research that people do in smart clothing. So I'm going to give you a few applications, and then I'm going to focus the second half on what I've been doing while I've been here in Loughborough. Okay, so I come from clothing design. I sit at the University of Minnesota. I sit in the School of Design, as my hosts do in the Environmental Ergonomics Research Center at Loughborough, which is a really interesting parallel. And my subfield of clothing design is what's called functional clothing design, which is kind of the branch that's more about what it does than how it looks. How it looks is also an important function, but it's pretty well by fashion, so we let that happen, and then we focus on the what else it does kind of part of clothing design. And the sort of seminal book in this area was written by the inimitable Susan Watkins, and she titled it Clothing the Portable Environment, which is a nice link to the Environmental Ergonomics Research Center, in the sense that we're thinking about the human environment and how we can kind of manipulate and mediate that. In functional clothing design, this is one of Susan's images, which I always love. It's somebody having a very bad day. The environment that we're trying to preserve or protect or support around the human can be influenced by a lot of different things. And as I sort of moved from functional clothing into smart clothing, the driving impulse was that we can do all of these things. We can protect and manage and provide all of these services to the human through clothing, but if we add electronics to that mix, then we can do a lot of that more dynamically. We can. The trouble with some traditional approaches to functional clothing is that you design a system that does one thing and has to keep doing that thing, even if the user's needs change. So if you have on a heavy coat, it's designed to provide a certain amount of insulation. If your, metabolic rate or your environment changes, the garment can't adapt. So bringing electronics into that allows you to do a little bit more of the responsiveness and to make some of those functions a little bit more dynamic. And that's kind of where I've come with smart clothing and some of what we'll touch on today. So I started working in smart clothing about 25 years ago, and kind of the first wave of wearable technology when people didn't know what that word meant. And back then there were kind of two major, I don't know, like groups of people that were interested in wearable technology or sort of driving forces behind wearable technology development. One was sort of coming from the soft goods side of things. Soft goods are things like textiles and materials that are soft. And it was I guess a broader focus on what electronics in things like fabrics could do, and maybe a little bit more of a focus on what electronics added to clothing specifically could do. On the other side, there was a group of people coming from from computing and computer science predominantly that were interested in what happens when you put computing hardware onto the body. Part of that was physical at the time because the computing hardware was quite big. And there were no smartphones. So actually putting the desktop computer onto the human body was a significant challenge in itself. But then in parallel with that, I guess the interest was what happens when that ability to access and process information is brought into the user's immediate environment so that it's with them all the time in whatever context they're in, and what happens to their needs for information and the way that you display it. Okay, so those camps existed. They kind of gradually converged, especially commercially, and they kind of settled down on the side of the spectrum that's closer to hard goods. So, those of us building things into fabrics, we're slightly less successful commercially. And there's a lot of good reasons for that. Putting stuff in fabric is really hard. There are several people at this university that know a lot about that. Putting things onto human bodies and distributing around a human body is really hard. When you localize something down to a sort of single point, there's a lot of benefits in durability, manufacturability, and even maybe some benefits in your interface design and like the cognitive human factors of being able to access information because of the ways that some of those points on the body are visible and things like that. So there's a lot of good reasons for that. At the same time, there's a lot of bad side effects. And most significantly, the biggest limitation is that when you localize to a single point, that becomes your window into the human. That becomes all you can know about them. And as we'll talk about mostly today, becomes all you can do. You can only do so much to change an environment when you only have like a wristband. So it really limits the kind of scope of what wearable technology can do. And I think as a field, we're still wrestling with how do we get back to all that potential. We made so much advance in terms of popular understanding of wearable technology and even, some of the information-centric applications as the commercial viability of things like wristbands exploded, but we lost this other side of things. And a lot of what I do kind of looks at some of those exciting applications as well as the reasons why they were difficult to commercialize. Okay, so we'll start with an example. This is one of my current passion projects. We've been working on a garment that treats neonatal jaundice. If anyone here have personal experience with neonatal jaundice, like your children, someone you know? Oh, it's nice. It's most babies. So more than 60% of babies are born and then develop some form of jaundice. So it's really, really common. It happens in the first few days of life. It's caused by a buildup of bilirubin in the blood, which your liver processes, but the newborn liver isn't ready to do that yet. It has been relying on the parent's liver, the birth parent's liver. And so when they're born, it takes a little while to get up to speed. It's very treatable. Almost all cases are treated successfully, except the really severe ones that are usually due to something else. All you have to do, surprisingly, is shine blue lights on the baby. It's not UV, it's not anything special, it's literally blue light. So very simple technology in terms of treatment, but the worst part about it is, and this is my daughter, she was 1 day old, Most of the current technologies for doing that are these overhead lamps and or a mat, a light up mat that sits under the baby. And the treatment, the efficacy is related to getting the right intensity of blue light and getting more of the body surface irradiated. So surface area is absolutely essential to this. She's really unhappy. She's crying. I'm one day postpartum. My baby is crying. I get yelled at every time I pick her up. For the more severe cases, it's actually like a really awful thing if you take them out of the lights. If you have a preemie that has really, really high bilirubin levels, they have to stay under the lights. And, parents tell me that they weren't able to touch their baby for a week, like after they were born. I had not ever hugged their own baby because they had to stay under the bilirubin lights. So it's very traumatic emotionally. Nobody's hurting. The baby's just really unhappy and crying. And also, if you can see, like there's a lot of her body that's in shade because of the way the lights are oriented. So the treatment itself is really not working as well as it could because of the way that we're manipulating the environment. So this approach to treatment takes the body and puts it in an environment rather than changing the environment that's around the body. So I had this experience. It was terrible, and I do what I do, and it's a really simple technology. So I was like, well, clearly, we can fix things. So a few years later, after COVID passed, I was able to pick my head up and start working on it. So we started working on this onesie that has a bunch of LEDs embedded, and it basically takes that light source and puts it right against the skin. So there's no calibration and dosage, user error involved. It doesn't hurt the baby's eyes because the eyes aren't irradiated, and it gets all the little nooks and crannies and crevices of the body. Incidentally, as we've been trying to measure this, we've also measured commercial devices and discovered how actually horrible they are. So we've been trying to, we had to build a custom mannequin to be able to measure radiance around the body. And, as we did that, we discovered that, very little of the body is reaching that prescribed dose with some of these devices. So like the prescribed dose is like 30 microwatts per centimeter squared. And this overhead light that we measured reaches none of the body at 30 microwatts. And even the wrap, which is a mat that you can kind of wrap around the sides of the body, it only gets to some smaller percent, like 12%, something like that. When you use them together, it gets better. The onesie right now is outperforming the two of them together. And we're still working on things like how to measure this. The mannequin and the lights alignment has some error in it. So we think actually the onesie is working better than we're able to measure right now. But it's working really well. When I talk to clinicians about this, and actually pretty much everybody, the first thought in their mind is like, why hasn't this been done? Like, this seems really obvious, right? It's not a very groundbreaking technology to wrap Christmas lights around your baby. The reason is it's really hard to make. It's hard to make scalably. It's hard to make in a way that will definitely pass the electrical safety requirements for infant medical devices. And it's hard for those two things not to destroy what's working about it, which is that it's soft, breathable, conformable, stretchable. So all the things that would make it cheaper to make or electrically safer are destroying the ability to conform and wrap around the body. So right now we're right in the middle of kind of developing that. This is a method that we use to embed LEDs where we basically stitch the traces like they're a printed circuit board, and then we use surface mount reflow processes similar to how you populate a circuit board with commercial LEDs to stick them on. Which works well, but there are very specific installation requirements for medical devices, and that is not it. So there's a lot of innovation we have to do, or we need to learn how to adapt manufacturing processes that are already scalable so that they don't destroy the critical functionality that we need from the soft circuit. So manufacturing, mechanical stability, durability, these are all persistent challenges in e-textiles and wearables. Okay, second example. So my lab, my co-director in the lab is Brad Holshoe, and he's an expert in shape memory alloy. Shape memory is a metal alloy that when you heat it up, you can sort of train it to a geometric shape. And then when it's cool, you can deform it like a wire, like easily. And when you heat it up to a lower temperature, it will reform that memory state. So we use it in textiles a lot to make clothing that changes shape for various purposes. A lot of those purposes are related to compression, so squeezing the body in different ways. And there's a lot of different medical and occupational reasons why you might need to squeeze the body. So we've been working on a number of different applications in that area. One of them is sports rehab and injury prevention. So think like a dynamic knee brace, something like that. So both as a haptic cue, like reminding you or telling you as you're trying to retrain a pathological movement, or as actually a physical support, loading the body so that your biomechanics is adjusted in some way to protect the joint. So this is sort of the general application you might imagine. Like you've got these leggings, they're going to make sure that the movement of your knee while you're playing a sport is monitored. It's going to cue you if it notices you're doing something that's going to lead to an injury, and or it's going to actually support that injury in the moment, so that you're getting the loading forces you need to correct that movement. That's very hand wavy. All those things are hard to do. So I'm going to walk you through a little bit of, what we work on, the facets that we work on, and what makes those interesting and challenging. Okay, so one of the first stumbling blocks we came upon in this domain was actually trying to understand how to fit this mechanical system to a human body. I come from clothing. We do things like create garment sizes. We think we do something called fitting. Sizing and fit are very big concepts in ready-to-wear clothing. Especially when you drill down to the level that you need for something that's very functional and has really precise technical requirements. So let's say, we're trying to engineer this garment that compresses the knee. We really need to understand what the body dimensions and geometry looks like, so that we can develop the shell so that when it compresses, it loads in the right way. So initially we thought, oh, well, we'll just measure it and then we'll find a sizing range so that it, if your circumference is this, you get this size of leggings, and then we'll pre-program it to, contract this much, and it will provide the right amount of force. That's how something like compression socks work, right? You have a small, medium, large, you decide what your leg is, and then it's on the package, it says, if you're lucky, it says something like, oh, this will provide 10 millimeters of mercury of pressure, which is a total guess and definitely not accurate. So maybe we could do something like that. So we started digging into the anthropometry and geometry of it, and the answer is no, you can't do that. The variability in humans is just outrageous. And I mean, I know this already, but when you really try to get down to like, is it a circle? It's not a circle. And if you're compressing in a circle, now you've got concavities that are not compressed, you've got protrusions that are getting too much force. So just trying to measure and characterize this kind of led us to the conclusion that you could do this if you body stand everybody and generate a completely custom garment for each body, which is prohibitive, or we really can't do this without more complex control strategies. So we started working a little bit more on the control of these systems. So this is an example of a knitted compression actuator. So it's just a little knit swatch right there. And this is actually not a pre-trained shape memory wire. This is a wire that wants to be straight, and you knit it into a looped structure. And then as you heat it up, it tries to straighten. And given the geometry of the stitches, and there's a lot of variability you can build into that just by the stitches that you use, it causes that swatch to change dimensions in one or two directions, depending on what you do. So it's just contracting, right? But just most of the time in the lab, how we actuate something like this is we put it in a little tiny thermal chamber, and we heat it up to a specific temperature, so the whole thing is nice and even, and it's all getting the same, thermal energy. And then we wave our hands about like, oh yeah, you could do this electrically. It's no problem. You just attach leads to it and run a current through it. It'll do the same thing. No, it will not, because that electrical path is going through this knit, and there's all these little intersections that are making shorts and creating that electrical path. And then as it contracts, they shift and change and move. And everything gets messy very, very quickly. Similarly, we also need to be able to control this with a soft sensor. And this is the sensor we're using. It's a capacitive multi-layer structure where we got like electrodes going this way, and then this one is piezoresistive. A resistive layer between, and then electrodes going this way, and then we're querying all the intersections to figure out how much resistance it has in each of the little cells, which tells us how much compression we have, in theory. Except they're textiles, and textiles never do what we want them to do precisely. So everything gets messier than we want to there too. Just to give you a sense, I'll give you the actuation and then the sensing on the control side. So this is what it looks like, the simplified version of what it looks like to actuate that knit. And I didn't show you the slide where we thermally imaged it to try to figure out where you place the leads, and if you switch between them, can you get more even thermal distribution? And the answer is no, it's kind of all over the place. But so given you're going to have a very, very, very messy actuation signal, can we try to model that? Can we extract some of the features of the noise and then be able to predict those and account for them in the control model so that we're more accurately getting the compression that we think we're getting? On the sensing side, here's we've done a lot of work in force sensing on the body, which is, much more complicated than you would think it is. So some examples of why that needs to be modeled. On the top here, you're looking at 4 of the same sensors. We made them identical. And as you can see, they are not the same. A lot of that is because of the variability in the materials we use. Like as they're manufactured, they have variability. And then as we build them into a matrix, it's not perfectly uniform, and the spacing is different, and the electrical path and the contacts are different. So each individual sensor has to be modeled and calibrated itself. Similarly, and this is something that's persistent in wearable force sensing. Most methods that you can use to sense forces on the body are sensitive to basically deformation. They're sensitive to all forces. So you want to sense this, but this is giving you the same response. So you take that force sensor and you put it around a curved body, and it's already biased. It already has a response coming out that you can't distinguish from compressive force. So on the bottom, you're seeing the difference in response from one sensor in 3 different curvatures. So we need to be able to account for what position is this sensor in, and then even more complicated, if you have soft tissue and you have like a point compression, you're now deforming it again. So there's a lot of noise to separate out. Not that this is impossible. So this is all work of one of my recent graduates, Alarosa, and he was actually quite successful in getting a control working. So this is a human soft sensor, soft actuator, and he's getting pretty close to actually tracking the force profile that he was trying to achieve. And this is the current level. This is the actuator being driven. So it looks like a mess, but it's actually a complex control model that's achieving the result that he wanted it to. All that to say, this is a band. This is a tourniquet. This is not leggings. So all that geometry we still need to go back and do. But you can see where some of these invisible challenges of wearables really pop up, and how if a company that wants to get a product out the door in the next quarter is really not going to be able to get over these hurdles in time. So that's where we end up with simpler and simpler commercial products while research kind of chugs along in the background. And then in parallel with that, so initially I started this section talking about, that idea that we could just fit it to the user, and maybe if we did better fit, then we could get better results. So I didn't really dig into a lot of the other forces we might be trying to sense, but like with dynamic movements, we're often trying to sense elongations along the joint, like from a bend of a joint. And even with that, and also with actuation, anchoring that force to the body, anchoring that garment to the body so that it experiences the force that you think it will, is also a persistent challenge. because we think that clothes, especially skin tight clothes, move with the body, like that's the point of them, right? But they don't. I mean, your skin doesn't even move with your body. Like if you rotate your arm, like it's going inside your skin. So even if we had it stuck to your skin, it's not moving the same way as your body. So do that again with a layer of clothing, we have even more coupling problems. So one of the ways we try to get around that is by anchoring that garment to the body so that we get a more accurate coupling between the garment and the body. But to do that, again, we need to understand the geometry of the body and then the surface garment. And we need to size that so that you can, manufacture it and sell it in some way that's still going to be accurate. So another recent grad, Eric, he actually had to do this because he was just trying to run a user study, like just trying to put these leggings on humans, and he had to know who he could recruit. So he's like, all right, how do I make a sizing system so that all my subjects are fit by these prototypes that I'm testing? And what he discovered was, well, you have to do really complex fit, sizing system engineering in order to get there. So first he needs to understand the variability in measurements. So this is a body scan database. Then he needs to understand the material assembly and the mechanics of each part of that assembly. Like the elastic around the waist is different mechanics than the leggings is different mechanics than where he's got anchors built in with a frictional interface. So he's going to have to do the mechanical modeling of those segments, then match that to the body dimensions. We know how much force is being exerted on the body by each part of the garment in order to know if this person actually functionally fits, not just like what their dimensions are. And then he's going to have to integrate all the different body dimensions, because humans don't grow like nesting dolls, like they grow in different ways, to be able to figure out which humans fit into which size. And then engineer the system to try to optimize for more people fitting into the existing sizes. But you can automate some of that, and he ended up with a system that uses 5 sizes instead of 7 and gets 75% instead of 58% of humans accommodated. So, an interesting way to kind of solve that problem of what size should you wear. And then lastly, another way that we've been kind of working around this, so fit is difficult. I didn't even get into like placement, like let's say you're trying to do an elongation, like this is a stretch sensor, a textile stretch sensor. And it matters a lot where you put it. If it's on the axis of a joint or slightly off axis, you're going to get a totally different signal from the sensor to the same body movement. And making a new garment for each individual is prohibitive, especially if you're something like a physiotherapist and you just want to be able to adapt it to the patient's evolving needs. So instead, we built this platform that's like, I don't know, 12 layers or something, where we have addressable traces on either side of the fabric. And then in the middle of the sandwich is a common ground plane. And we use this interesting little twist conductor that has kind of a barb in it that you twist it in, and it passes the barb through the fabric, and it does both the mechanical and the electrical connection. So basically you would take this little connector, place it on one of these stripes, which are the addressable traces on the surface, and there's a similar on the inside of the garment. And then it would make contact with there's 2 barbs in each connector. So one barb makes contact with the addressable trace, one makes contact with the ground plane, and now you have something in a circuit. You wire that up to your microcontroller, and you can change what components you're using, you can change where they are, and you can like customize that whole system to one user without having to build a new system every single time. So the e-textile system design of that is its own challenge. Right now, these are very stiff leggings, so they need to be stretchier, they need to be softer in order to be kind of deployable. But the concept gets us closer to something that like a physiotherapist's office could use for any patient. Put these on and I'll give you the cue you need. I'll train the system to respond to your specific gait, whatever it is that you're trying to achieve for that specific patient. Okay, so shifting gears here, I'm here because of a different part of the immediate body climate, the thermal microclimate. So I don't know, many of you already know this, but maybe not everybody does. You have like world leaders in human thermal physiology and thermal environments here at Loughborough, and that's why I'm here. because they're really cool. And they're really great equipment. So I've been playing for the summer. So I'll take a step back and tell you how I got to this project before I get into what we did together. So this kind of started because this back of the envelope calculation because I got curious one day, like how much energy do we spend on heating spaces versus how much energy do humans, like if we are little radiators, like who's more powerful, us or the ones in the environment? And I thought like we'd be like nowhere near, our bodies would be little sad radiators and we have these big powerful HVAC systems in our environments. So I kind of did the back of the envelope math and like the stats in the US, what the energy we spend on heating spaces are very accessible. And it's like one of the leading sources of energy consumption by category is heating, like indoor heating in cold months. Cooling is much less energy intensive and also much less likely to use non-renewable sources. So we use about 4 quadrillion BTUs a year to heat the US. The humans make 5 quintillion BTUs. We are better. And not all of that is in the winter months, of course, but I had no idea that we were such powerful heat sources or that we were wasting so much heating environments. So if you think about, all the spaces that are heated during the day and there's nobody in them, like your home, or even in a big building, all the offices that are empty or the classrooms that are empty, and we have to keep them heated, especially in older buildings where there's a lot of latency. You can't just like snap your fingers and make it warm. Like you have to, my house was built in 1900 and it takes like an hour per degree to change the temperature in the winter. Like you cannot just like turn it on demand. So, it seems like we could do a better job to use this resource and minimize the environmental resource. In addition to that, all of you who have shared a thermal environment with other people know that preferences vary widely. And nobody is ever, like there's never, consensus and everybody's pleasant in one thermal environment. And there are serious consequences to that. Cognitive, especially, being thermally uncomfortable is very distracting and it degrades your performance. There's some physical consequences if things get more extreme. So it would be better if we could customize, right? We could bring this with us. And again, heated clothing, not a super new concept. Like as far as like brand new technology, it's not a super new concept, but it's not common. So why? So I started doing some work with, we have a Center for Sustainable Building Research in my college. And so they're the experts on the building thermal environment. And I kind of wanted to know, like, is this really, what kind of savings would we have if we moved the heating onto the body? So we did a little bit of modeling and it quickly became apparent that not all environments are equal. So there are some environments that would be really high potential if we could turn down the ambient temperature, like a warehouse where there's like 4 or 5 people in it and it's an enormous space. If we could, turn the ambient down by 5 or 10 degrees, then, we would have a huge energy savings in that kind of environment. Versus a brand new house, which is more densely occupied and better insulated, we would have less savings. So we're kind of trying to navigate the design space. Who are the people that we are trying to serve? What are their like environments? Like what is the range of temperatures we're trying to address here? And what are they doing? How can we design insulation that's going to work? We also did a study, my students and I, where we took some commercial heating devices and tried to manipulate what we call the thermoneutral zone. So like pretty close to indoor temperatures where you're like a little too cold, not like winter outside, but like a little too cold inside, to see like, which devices would have more bang for your buck in terms of making people comfortable. And you don't really need to parse this complicated figure, but the point is that it's all over the place. Especially in the thermoneutral zone, which is kind of very chaotic, both like physiologically and psychologically. People just don't have the same preferences. They don't have the same physiological responses. They don't, perceive their skin temperatures in the same way, nor do they prefer them in the same way. So it was just very difficult to find a signal, to find a consensus that we could use to control the system, to design the system. To kind of get into some of why that, I've mentioned a few of these already, but some of the variables that are influencing this, thermal experience is very psychophysical. You know, there's the physical environment and your physical skin temperature, and then your body is manipulating that with its own physiological processes, which are not the same individual to individual. Then you are sensing that, like the actual thermal experience. And you know, how sensitive are you to those changes? And then there's preference on top of that. Do you like that you feel cold or not? And all of that is variable between individuals. So that adds some mess in there. Oops. I mentioned that part already. We again, from the control systems perspective, we don't really know how to control this. Like, is it just that I want to get the garment to one input temperature? Or like, what is the loss between the heated up thing and the skin that is maybe or maybe not touching? How is that going to be dispersed throughout the body? Because again, like, we're not just a static thermal mass, like there's blood circulating and moving the heat around. And do we want to measure the skin temperature, which is what most existing thermal comfort models are based on? Is that even useful when you're changing the skin temperature actively by heating it? And is that the same as your skin temperature changing by itself? So there's a lot of, you know, challenge in there. And then again, coming back to that application, if we know what you're doing and who you are, that changes a lot about how we design the insulation. Can I ask you to wear gloves? Can I ask you to wear a thick coat? Or will you only wear short sleeves? You know, that's going to really change where we can deliver heat to. And these are all variables that are just not well characterized for the heated clothing space. So in parallel with that, we were also developing the ability to generate heated garments, because when you're limited to what exists on the market, you don't have all these variables at your disposal. You can't change where the heating is supplied and how much it's supplied and things like that. So we did a bunch of work to develop some heated, resistance heated textiles and figure out the materials and the way that heat transfers through those materials and which materials we might use to be most efficient and things like that. And we got to, you know, some initial prototypes. And then sort of the next step would be like, how do we test these? And we already knew that it was really hard to do with humans. So I really didn't want to have to do it with humans again. So the EERC has some very compliant mannequins that are easier to force to do uncomfortable things. So this is sort of where this collaboration started on my side. Was, you know, an acute interest in like learning how to use this kind of equipment and the limitations of it, and sort of what you could do with it when you were trying to measure heated clothing. So EERC, if you're not familiar, has two heated thermal mannequins. One has an active cooling system and one does not. And the mannequin can sort of regulate its own temperature and then measure the energy that is being transmitted from the mannequin, basically, and then through the clothing system. So if you can control the environment, you can control the mannequin, and then you can measure something about the heat transmission. Now, typically, I think the most common application is for testing passive clothing systems, so regular clothes. Again, and this is like a theme in my life, like, you're not supposed to do that. This is not how you use the machine. So we had some trouble with the active heating part of it, because now you're adding another heat source. And in order to measure like the insulative value of the garment, you need that mannequin to still be on, like still be generating its own heat. And if you heat it so much that it doesn't need to do that anymore to reach the predetermined temperature, then you can't measure insulation anymore. So this is all to tell you why I've had to spend a lot of time in a negative 20-degree chamber. It has to get really cold in order for the mannequin to still be heating itself. So when I got here, we did some tests with our older prototype there. And you know, that one was old enough that I was able to like test it to failure and things like that, burn out a lot of the heating panels, just to kind of establish the range, you know, how high can we go before everything breaks down? And what chamber temperature do we need before we lose that heat flux from the mannequin? And finally got to a method, which last week was the week that I kind of intensively collected as much data as possible, and now I'm collecting the dribs and drabs and things that went wrong along the way. So basically, this is a thermal liner. This is a It's basically like a one layer garment that has heating zones like you saw in the swatch all over it. As much of its surface area as possible is heated. And it's controlled in zones so that I can activate them one by one and start to see where on the body things change. And because the garment doesn't fit the body the same way in like, a sleeve wraps all the way around and like contains that heat better than the bottom where it's a little bit open or the top where it can come out. And whether or not it's like the concavity of the lower back is different from the convexity of the upper back where it's touching the skin a little bit more. So that's the liner. It zips into a fleece layer, so like one more layer of insulation. And then we put a windbreaker shell over the top of that for another layer of insulation. And what I'm trying to do is, initially when I thought of trying to get these guys to collaborate with me, my brain thought that we could take this mannequin and be like this perfect human, and it would just be a very standardized human and have all this great physiology in it. That's not really how that works. Physiology is really complicated, and designing a mannequin to really imitate that is also really complicated. So where we've arrived is trying to measure the local insulation of each of these zones in each of these conditions, so that I can start to map that against what is known in the literature about comfort and insulative value of clothing. So if we know that, other studies have shown that you should be comfortable in this temperature in about this much insulation, now I know how much insulation that equals in this system. So I know if I turn the heat up, I'll get you to this level of insulation, or if I leave it down and add a layer on, that will get me to the same place. I basically have a characterization of my design parameters. So as we navigate who needs this, I can make a decision. Like if you're, processing food in a frozen foods factory, maybe you're happy to wear a coat all day long. If you're working in an office, maybe you will not wear a coat. So, that tells me, but maybe in an office, you're sitting next to a wall outlet, so I can turn it up as high as I want. Versus if you're walking around a factory floor, I only have a battery, so I need to conserve that energy a lot more. So basically, I'm hoping to come out of this summer with a map that we can then use to navigate and try these things on humans in order to build those more detailed control models that get them to comfort. Like this tells me the ballpark to aim for, and then we can drill down into how do we adapt that signal so that you stay comfortable. So some early results, we're seeing what you would expect. This is the 2-layer condition, and you're seeing the different levels of heating power I'm supplying to the garment in each different zone. And it's measuring the heat flux from the mannequin, which I will then map to insulative value of that area. One of the challenges is that the mannequin zones and the garment zones don't line up perfectly, so I need to do the area conversion in order to be able to compare across them directly. But we are able to max out. So even in negative 20 degrees, we do max it out so that, at 30 watts, some of those zones are the mannequin is no longer supplying heat, which I don't know if I can totally convert to like, you'll definitely be comfortable. But, it's nice that we've been able to get to that limit, because one of the things I really wanted to know was like, how low can you go? How cold of an environment can heated clothing really overcome? Which gives me a boundary on, applications that we could pursue. Okay, and then another fun thing I've been working on. For a few weeks, I was like, let me just go in there and I'll just do it for fun. So we did have a day where I turned it down as low as it would go and went in there in a t-shirt just to try to see what happens to my body. And I'm from Minnesota, my husband is going, Lizzie, like you've experienced these temperatures every winter. Why do you want to do this? Okay, but I didn't measure it. And also it is totally different when you are in the middle of a heat wave. That sounds fun in a heat wave, negative 25, versus when it's the middle of Minnesota winter, negative 25 does not sound fun at all. So I only lasted 15 minutes, but my fingertip there was, let's see, 13.9 when I went in the chamber, and right before I came out, it was down to 4.4. So I haven't processed all the surface temperatures or anything yet, but yeah, I was really curious to see what happens to me. And one of my nice to haves for the summer is if we get time, I'm going to try to do something similar, but with the heated jacket on it, see how I feel. just to kind of take one step towards those human comfort perception trials that I ultimately want to be able to do with this kind of a system. So I'm getting close to the end here. So let me sort of leave it there. This is some of the students and colleagues whose work that I focused on in this and some of the grants that I need to acknowledge. I also will leave you with my two shout outs. If you like functional clothing design, there's a great book about it. And if you work in a different discipline and you think wearables sounds interesting, we have this 1-year graduate certificate that I think as of now should be able to be accomplished online. That's designed to help people bridge between different disciplines. So we will leave it there. And if there are questions, after that.